All right, so I have some definitions here. We're talking about patterns and linear functions, as we saw from the video.
Oh, we can't start.
I am starting.
I can't.
Oh, you can.
Wait, hold on.
I'll leave it up. I'm recording it, so you can even watch the recording. Dependent variable. Here's what a dependent variable is. You can go back and forth, right? You can do both. I'll bet both of you can do both. Dependent variable is changes in response to another variable. So dependent means it depends on the other variable. So if we plug in a number like 2 to an equation, we get a different response than if we plug in, say, a 3. So it changes in response to another variable. We call that the output. Make sure you put output on there. Dependent variable is the output. Oftentimes in Algebra 1 we use x and y is usually the dependent variable. It's telling me my computer is running slowly. No kidding. Thanks for letting me know what I already know. So changes in response to another variable output. The independent variable, if this is called the output, this is the y, the x is called the input. We have genius in our midst here. So it doesn't change or depend on another variable. So typically in Algebra 1, it's x. I'm saying in Algebra 1 because we use x and y primarily in Algebra 1. And as you move into other courses like Algebra 2 or Pre-Calculus or Physics, we use other letters to represent the dependent and independent variable. And so actually, this lesson and the one on Monday, we're going to be talking about functions. But today we're looking at what are called linear functions primarily. Actually, that's all we're going to look at today are linear functions. But a function is a relationship that pairs each input value with exactly one output value. What? So we're going to take each input value, like if you plug in a number like 2, you get an output. If you plug in 3, you get a different output. If you plug in 4, you get another output. So it's a function as long as when you have a given input, you don't get 2 outputs that are different, one stacked on the top of another. Like if you plug in 2 and you get 3, and then you also could plug in 2 and get 4 as well, and that would not be a function. You kind of saw a scatter plot of points in that video that was showing that relationship between temperature and snowmaking, or water needed for snowmaking, and that was that scatter plot was what we call a linear function. So a linear function is a function whose graph is a line, but not vertical. So the dependent variable in these examples down here will be the x, or the independent variable, sorry. Independent variable will actually be the x, and the dependent variable, the output, will be the y. So we're putting in x into the equation, and then whatever that function, we call those function machines, that's what this is all about. These are function machines. You have a given input, typically in Algebra 1 it's x. And it goes into the machine, gets worked on, and it comes out as what's called f of x or y. That's what that says. That's f of x or y. I should probably write that down here. It's f of x. Here's how we say this. F of x. So it's the function with x plugged in as the input. That's what this means. F of x. Doesn't mean f times x, it means the function with x plugged in. or we call that y. So if I plugged in 3 to this function here, if I plugged in 3 to that function,
What just happened?
What did you, Hunter?
right. So if I plug in 3, go ahead and do the algebra here. If I plug in 3 to this particular function, what's my output going to be? In other words, if I plug in 3 for x, I'm going to get 10. Yeah, it looks like this. 3 times 3 plus 1. So I'm plugging 3 in for x, and you should get 10, yes. All right. So on the next one, plug in -2 to the function machine. Plug in -2 to the function machine. -2 squared is going to give me 4. Yeah. Good. Yes. Briggs, guys. Okay, so whatever the function is here, whatever the function is, you want to make up your own function? What's your favorite function? Everybody should have a favorite function. I have a favorite function.
Not very well.
No. It's 3x minus 2. That's my favorite function. It's a linear function. It's got a slope of 3, y-intercept of -2. Yeah, great function. So if I plug in this function, 3x minus 2 is my favorite function. Okay, you guys pick an input or an independent variable. Pick an input here. One. Okay. Ooh, a difficult one. So plug in 1. So if I plug in 1 here, then I get an output of 3 minus 2, which is 1. Oh, look at that. So as the function changes, and as the inputs change, the outputs will change. So I'm going to give you some examples. I'm going to give you guys some examples of some linear functions, okay? So I'm going to do that in a table and picture format here. Any questions on it so far? What I'm asking you to do is plug in a certain independent variable into the function, and then out comes the output. This is called a function. That's it. That's all we've talked about so far. So, all right, guys. Okay, guys, we need to refocus up here. I know we're distracted. Refocus up here.
They're the worst.
All right. So it says in the diagram. What is the relation? I can't talk over you here. I'm going to wait till it's quiet.
Okay, quiet.
Here I am. Ready to go. I'm still here. Okay. So, here I have a rectangle. I have a rectangle. And the rectangle has a perimeter. You remember how to find perimeter of a rectangle?
Yeah.
How many lengths of 6 do we have here?
2.
Notice in each picture, I have 2 6s. Do you see that? 2 lengths? But what's changing each time? What's the variable?
A 1.
The 1. The 1s are changing each time. There's more of them each time I add a rectangle, right? So that's the variable. So,
Really? That's what
Please stop talking. Thank you.
okay. So, when we fill out this table, we're looking for a pattern. I've already told you the pattern is going to be linear. That's this whole section that I'll list them, okay? So right here, it says number of rectangles. In the first picture, I just have one rectangle. So
Sit down, Tony.
So, alright, so what we're looking for is a pattern here. It will be a linear pattern. We'll see it when we graph it, okay? So with one rectangle, I have only one width here and one width here. So it's one goes into those parentheses. So you'll see a little set of parentheses. We're going to take 2 times the number of widths. 2 times the width of 1, I should say, plus 2 times the length of 6, and that will give me the perimeter. So 2 times 1 is 2, plus 12 is 14. And the ordered pair is the 1 for the number of rectangles, comma, 14 for the perimeter. So we have a collection of points here that is, as the width changes, as we add another one to the width, another rectangle to the width, then what is the new perimeter? So we're looking for a pattern. It will be linear. So with 2 rectangles, we have 2 times, okay, with 2 rectangles, I have 2 ones, right? So it's now gone from a width of 1 to a width of 2. And what doesn't change is the lengths. So I have 4 plus 12 is 16.
Oh, shoot.
And so my new ordered pair is not 1 comma 16, but 2 comma 16. Oh, there it is. Forgot I had it there. So we have 2 comma 16.
What?
Forgot I had that there. So here we had 14. Here we had 16. And the next one, when I put in 3, now I have 3 rectangles. So we have 3 across as my width. So 2 times 3 is 6, plus 12 gives me 18. What do you notice is the pattern here? Maybe you can figure out the next one without even doing the arithmetic.
2.
When I go to 4 rectangles, it goes up by 2. So I go to 2 times 4. This becomes 20, and my new
420.
coordinate is 4 comma 20.
420.
So it's going up by 2, you're right. When you see the y variables going up by a constant rate, that shows that you have a linear pattern. Okay, it shows a linear pattern there. What is the constant rate? What's the constant rate that we're going up by on the perimeter every time we add another rectangle? 2, because you add an extra 1 here and an extra 1 here. All right, so in words, each time we add an extra rectangle, our perimeter goes up by 2. We'll say the perimeter increases by 2. And then we're going to be asked to write an equation to go with that table and that description in words. So it says each time we add an extra rectangle, the perimeter increases by 2. So you can see the makings of an equation right here in the table. The variable is what you see in red here. It's the number of the new width when I add a rectangle. So if I replace, you see in parentheses, the first set of parentheses here, that number is varying. We call that the variable. We'll call that x, okay? So my equation is y equals 2x plus, what is not changing in each of these as I go down?
6 and 2.
And what is 6 times 2 equal?
12.
12. So that is called we'll learn more about that later, but the y-intercept.
Just graph.
Yeah, and then we're just going to graph it. Now you don't need to connect the dots. because we're doing what's called a discrete, not continuous graph. A continuous is one when you connect the dots without lifting your pencil. It makes a continuous line. Discrete just is a whole set of dots. They might be in a line, but we're not going to connect them. So the first ordered pair is 1 over 14 up. So this is kind of like what you did with the pumpkin last time we were here. You were plotting points. So there's 1 comma 14. 2 comma 16, so go over 2 and up to 16. And you should notice, if you're graphing it correctly, that it makes a linear pattern. 3 comma 18, and then 4 comma 20. So if I were to connect the dots, I would have a line. So in today's lesson, if you go to do a graph, as I'll ask you to do, and one of the dots is not in line with the other ones, you've probably made an arithmetic error or a graphing error, okay? Next week, we'll talk about what are called nonlinear functions, functions that curve up a little faster, do other things, that curves rather than lines. But primarily in Algebra 1, linear functions are probably the most commonly, that's what we study the most. It's a big idea, is to understand everything about them. How to find slope, y-intercept, x-intercept, how to write equations of lines, things like that. Any questions on that?
No.
Got a graph?
Yes, next.
Ready.
Oh my God.
All right. It says in the diagram, what is the relationship between the number of triangles and the perimeter of the figure they form? So similar to the last problem, but different shape. Represent the relationship in a table, words, an equation, and graph. So doing all the same things again. So the first one, number of triangles, we've got 1 triangle. When we have 1 triangle, we have a pattern that's going on here. We have 4 times the number of triangles plus 2 times 3. You'll notice through the whole set of pictures here, how many 3's are there in this one?
2.
And in this one? 2, and in this one? Okay, so it's just, that's what's not changing, okay? That's the fixed amount. But what is changing is the number of 4's that you see in here. So here I have 1 4. 4 times 1 is 4, plus 6 is 10. So it's 10. So the first ordered pair is 1 comma 10. You'll notice a slightly different pattern here from the last one. When we have 2 triangles, when we have 2 triangles, how many 4's do I have now? Just 2 here. Yeah, it's going to be a total of 8, but we have 2 triangles for a total of 8 added to the perimeter. 4 times 2 is 8, plus 6 is 14. So you'll notice the pattern looks a little different here. What about the next one? Yes, here I have 4 times 3, which is 12, plus 6 is 18. So I have 3 comma 18 for that one. And then we have, for 4 triangles, we plug 4 in there. 16 plus 6 is 22. So I have 4 comma 22. So the pattern is there still a constant rate change? You see a constant change in the rate in terms of what's happening with the perimeter? Yeah, it's constant. What is the constant change here? Or constant, we call it a difference. The constant difference between the perimeters is 4. So that is what we see when we have a linear pattern, okay? A constant difference here as you go vertically down the table. So let's describe in words what's happening. Each time I add a triangle, I add how much to the perimeter? Yeah, each triangle adds 4 to the perimeter. You think you could write an equation for this based on my table? Y equals 4x plus 6 is correct. We have 4x. X is the variable. That's what we see all through here. That's what becomes the x. Plus 6. 6 is fixed. And then we graph this thing. So first coordinate ordered pair was 1, 10. The next one was 2 over and 14 up. Then we had 3, 18. Then we had 4, 22. So there's our linear pattern. On today's classwork, I'm going to ask you to figure out what the equation is to go with the table. So you fill in the table, okay, and then figure out an equation to go with it. The trick on these is to look at this, look at the pattern here. You'll notice, look at the difference between these two. It's 4, and look at where the 4 shows up down here. It's the multiplier by the x, right? So the difference is 4. If you look at the previous one, look at the difference here. It was 2, right? And these were going up by 1. As long as these are going up by 1s, and the 2 is the multiplier. Okay. So let's look at one more. It says representing a linear function. The table shows the relationship between the number of photos x you can take and the amount of memory y in megabytes left on your camera. Is the relationship a linear function? Well, we could probably answer that. We're only studying linear functions today, so it will be. Describe the relationship using words, an equation, and a graph. So, in words, what's happening as I start taking photos here? So I have no photos. My memory starts at 512 megabytes. I take one photo. What just happened? Yeah. So each photo does what? Yeah, it takes away 3 megabytes. So if I write an equation for this, what do you notice is the constant difference as we go down that? Yes, it's -3, -3. We keep going down by -3. So when I write my equation, where's that 3 going to come in?
Right now.
It could right now, yeah. But this time it's not a positive 3 because it's taking away. It would be a -3. Where am I starting at here? 512. So we could write 512 minus 3x, or what we'll learn when we start talking about slope-intercept form of the line. Have you ever heard of that? Slope-intercept form of the line? A couple of you remember that? Did you do a little bit of that last year? So in slope-intercept form, we would write this as y equals -3x plus 512, where the -3 is the slope, or rate of decrease here. So then this graph is going to be a linear one. It's going to look like that one in the video. It starts up at 512, and when I plug in 1, I get 509, and then if I plug in 2, I get 506. Plug in 3, I get 503. So that one's coming down. I already set up the XY axis. When you guys are asked in your classwork to graph these, you're going to have to decide how to scale it. So you want to scale it appropriately. Okay, so like here I have 1s along the bottom, but I wouldn't want to go by 1s up here. That'd be ridiculous, right? So I jumped up to 500 and then went by 1s from there up to 514. So when you draw your graphs, you might have to scale it appropriately. And we're only showing the first quadrant. This is called the first quadrant. With real life problems, we're usually just working in the first quadrant, positive x, positive y. Okay.